Hello, everybody. For the last time this semester, hope you're all doing okay and your studying is going well. Um, so tonight is just for questions or whatever you want to talk about, whatever you want me to help you with before our exam on Wednesday. So I have the chat open. I have Discord here as well. Whatever is more comfortable for you, go ahead and submit whatever it is you'd like to discuss, and we'll get started from there. While we're waiting for that, I guess a couple things about the final. The exam itself doesn't open on Blackboard until 12 o'clock on Wednesday, so there's no need to get there like super early. Um, Whenever we'll start around noon. If it takes a few minutes to get the computers going and stuff, that's fine because the exam will start counting time once you click into it. So there isn't too much of a rush there. All right, so first quest, can I go over hydrolysis and dehydration reactions? Yes, definitely do that. Let's see. All right, so there are several different types of hydrolysis and dehydration reactions that we looked at. Let's take a look at kind of the general form of those, and then we'll look at some of the different examples for some more specifics. So, in general, hydrolysis is the breaking of bonds by adding water. So, hydro is water, lysis means to break. There's various types of bonds that we're going to hydrolyze, but a couple common ones are esters. So, this could be whatever. This could be whatever. I'll just say CH3 for now. And so we can hydrolyze by breaking this bond. So not the carbon double bond to oxygen, but the other bond next to it. And that's going to give us. So the way to find these products is you just just separate the things. So we got the C, and then we've got the O and the CH3. Everything else stays the same. We're just separating those two things. And so then we need to add water to make sure everything has the right number of bonds. So we're going to add the OH to one side and the H to the other side. So those are our now two products from what was one molecule. Now this could be other things as well. Let's look at some other types of hydrolysis. So you could have an amide, meaning a nitrogen. So like you could have protein hydrolysis or something like that. Same idea. We're going to break that bond. Put the OH on. This time there's an N over here, so that's what gets the other H. But you can see that it's a very similar process, just the atom changed. And the only one that's a little bit different then is when we see hydrolysis of carbohydrates. The reason for that is you've got some sort of a ring structure that's connected to another ring structure. There's going to be lots of other stuff going on there too, but just as an example, the connecting bond is what's hydrolyzed. And with these, actually, it doesn't matter where you break it because either side there's not a carbonyl there. So you can break it here, you can break it over there. And we're going to do the same thing. So we're going to have our ring. That's going to become an OH. Then there's going to be an OH on the other side as well. So we've added water to there. So again, same process, just we don't have the carbonyl group in this type of a functional group. So any hydrolysis is going to be similar to this. You break it, you put the OH on one side and the H on the other side to make sure everything has the right number of bonds. Dehydration or condensation reactions are the opposite. So dehydration or condensation, you're starting with two molecules, you're putting them together, removing water, and ending with something that's connected. Um, so, for example, with lipids, you can have glycerol like that, and then you can have a fatty acid with a whole bunch of carbons on it. And rather than cut it, we're going to bring it together. So the OH from the carbonyl and the H from the alcohol are going to become water, H2O, and then what's left gets connected. So here, rather than redraw it, let's use our magic of technology and actually just get rid of those things. And then, so then what's happening here? Oops. Well, okay. We'll just leave it red. So then this carbon is going to connect to that oxygen, and now we have an ester. And if that so this would be a monoglyceride. And then if we put another fatty acid on it over here, it would be a diglyceride, and a third fatty acid could be a triglyceride. Or we could put two and have a phosphate over here and have a phospholipid. So things coming together, you get rid of water and then connect what's left. That's dehydration or condensation. Hydrolysis would be breaking things apart and then capping with H and OH. So adding water to break things apart. If you want some more specific examples of that, you can look in some of the, especially the more recent handouts that we looked at. So for example, with the proteins, there's an example here of the condensation or dehydration to make the protein chains using the amino acids and condensing those together. And there's similar examples in the lipids chapter, in the carbohydrates chapter, and in the molecular genetics. The book online also has some examples there. Is that helpful? Is there more you want to see about those? And let me know if there is. Otherwise, if there's something else you want to talk about, go ahead and post that. All right, so whether an amino acid has a basic side chain. Yeah, good question. So let's take a look. We're actually in the right handout here. So specifically to your question, with threonine and asparagine, let me pull those structures up so we can see them. So the reason that those two are not, so here's our threonine. I believe it's the O. It's that you're thinking about the OHs here, right? So we've got OH with threonine, and then the other one I think is up here. Oh, that's an amide one. Okay, so I could see how you might think that that is a basic side chain. I think that that's reasonable. If we look back at because of the nitrogen there, OHs are generally not basic. So we're not usually going to have any kind of base type activities from that. I just want to pull up the that table in the book where you can see that, so we can talk a little bit more about why those come out the way they do. Let me see if how I pull it up on the screen. All right. So I think what that question was asking, and maybe it wasn't a great question, I should take a look at it again. It sounds like one that I didn't write. But generally, we talk about basic side chains. We're talking about the negatively charged side chains. So the side chains that are like a conjugate base of something. But you're right that there could be basic activity when you have a nitrogen, although amide nitrogens are not particularly basic. Generally, what we are talking about when we're talking about basic is those negative charges, because what those are going to do in the context of proteins is any of the negatively charged side chains can attract the positively charged side chains and create that tertiary structure. And so that's the important interaction there, that the negatively charged or basic ones can attract the positively charged or acidic ones. But there's also, I mean, yeah, I'll go back and look at that question because I don't know that that was a great question, but this is what it was referring to, I believe, that we want to think about how those things would interact in the protein. All right, and then to review functional groups. So let's pull that up while we've got this here. So with functional groups, as we've said a few times, there's no like magic conceptual thing to figure out here. It's just really a memorization exercise. So you have to be able to identify different functional groups, which means you have to know what they are called and what they look like. So whether it's flashcards or some sort of a online game or practice or just writing notes out, there's this list of functional groups and you need to know what they are. So whether that's alcohols, ethers, amines. For specifics, if you go to Blackboard, let's see if I can pull this up here. Yeah, where's okay, so looking at the objectives here, you can see the specific list of the functional groups that you need to know. So you should be able to identify any of these functional groups in a chemical structure. And probably the hardest part of those, or the thing that's trickiest and trips people up the most, if I had to pick something, would be differentiating the carbonyl-based functional groups from the non-carbonyl ones. So, for example, well, here, as long as we're here. For example, here are some amines. And we can compare those to an amide over here. So look at the difference between the amine and the amide. Any NH thing would look like it's an amine, but you have to look around that particular part of the molecule and make sure there's not a carbonyl group, because the presence of that C double bond O carbonyl group now makes it a different functional group. And that's the same thing with, for example, alcohols and carboxylic acids. An OH that's connected to just regular single bonded carbon or even double bonded carbon or other types of things is an alcohol, but an OH that has a carbonyl group right next to it is a carboxylic acid. So that whole thing is the functional group. And the OH that's a part of a carboxylic acid functional group is not an alcohol. It's part of this other functional group. So that's probably the most difficult thing besides just knowing the names and the structures, just the memorization part of that. The trickiest part is if you have memorized it, just recognizing when it's actually something different. A similar issue comes up with ketones and aldehydes. They're both carbon double bond to oxygen, but the aldehyde has a hydrogen on one or both sides. A ketone has to have carbon on both sides of the carbonyl. So if you're only looking at the C double bond O, those look the same. And the thing that makes them different is the other things that they're directly connected to. So make sure with the carbonyl functional groups that you're looking at the atoms one away from the carbonyl also. That's probably the trickiest part. And again, the other part is just the memorization. You have to know the names and the structures of the different functional groups so that you can identify them. And some good practice is to take some big molecules like this, like we did in class. We picked out a pharmaceutical of some sort and pulled it up and found all the functional groups in the structure. That's a good way of practicing this. Trying to find all those functional groups in molecules. All right. Anything else on those points or other things that you want to go over? The side chains in the textbook, I don't know if were they blue? I don't remember. They're blue in the notes. Yeah, they're blue. Yeah. So those are the side chains. Let me look that up because I'm not entirely. There may be another way of talking about these that I'm not thinking about here. Um, all right, so I found another reference. Yeah, that seems more what I remembered. Because here's the issue with these negatively charged R groups. It really depends on the pH of the solution, and often aspartate is actually aspartic acid. It has a hydrogen. So these are actually carboxylic acid functional groups on the end, which aren't particularly basic. So they are charged in this case, but it would really depend on the pH of the system. So I I think this categorization is not um, doesn't really make sense in that way. Um, I think it's actually the opposite, which is a little weird. But the textbook that this particular piece comes from, they're looking at it a little bit differently. Generally, the basic ones are these that are actually shown to be positively charged here, which is why that threw me off a little bit. Because normally a base would be negatively charged or neutral, depending on pH. But all these nitrogen-based amino acids, these three, lysine, arginine, and histidine, those are more basic in that they've captured a hydrogen. So each of these has captured a hydrogen from something else. So these are kind of the conjugate acids being shown in this particular table. That's why that threw me off a little bit. So these are really the basic amino acid side chains, and these are the acidic ones over here, which is, and this table is confusing because they're shown in their conjugate bases and conjugate acids. It's the nitrogens that make these basic. We know ammonia is a base, and so the amino acids that have nitrogen are also going to be basic. So going back to your first question, the reason that asparagine is not basic is because this isn't really an amine, it's an amide, right? Because it's got the carbonyl, like we were just talking about with functional groups. So asparagine and glutamine are not basic because those nitrogens are not amines, they're part of amides, and amide nitrogens are not really basic. Whereas free nitrogens like these, so that's just a regular amine. That's an amine with this other piece here, which is a little bit different. Those act more as regular bases. So those are really your basic side chains. However, depending on the pH, they grab hydrogen, and so in the protein they end up being positively charged. So that's kind of confusing, and I can see why you'd be thrown off there. Does that help at all, or is that just more confusing? Okay, good. All right, what else? Hopefully all the studying is going well and everybody's ready for the final. The final is 67 questions, I believe, around there. 64, 60, something like that. Mid 60s. Is that it? Everybody's good? Oh, here we go. Okay, one of the objectives stating the difference between a strong and weak acid and a strong and weak base. Yeah, the key there is that strong and weak, those adjectives, refer to the electrolytic behavior of the solution. So a strong acid is a strong electrolyte, meaning it breaks up entirely into ions. A weak acid is a weak electrolyte, meaning it's only a little bit ions and still a lot of neutral molecules. And then base is the same way. A strong base breaks up entirely into ions. So something like sodium hydroxide that would break up into sodium ions and hydroxide ions in water. A weak base is something like ammonia, which would make ammonium hydroxide in water. So just some hydroxide, not entirely ionized. So the key there is that in our brains, we want strong and weak to refer to things like danger or corrosiveness, like how much it's going to burn your skin, when actually those definitions refer to how much it makes ions. Um, so strong acids are ones like hydrochloric acid, nitric acid, sulfuric acid that completely break apart into ions in water. So you put HCl. HCl is a gas, by the way, in its pure form. You dissolve that in water. There are no HCl whole molecules in that water solution or in that aqueous solution. There are just hydronium ions and chloride ions and water molecules. As opposed to a weak acid like carbonic acid or hydrofluoric acid or acetic acid, where you dissolve that in water, you're going to have still a lot of whole acid molecules and just a few hydronium ions and whatever the conjugate base of the acid is. So So just remember, strong and weak acid, strong and weak base, it's referring to electrolytes, not something about the danger or reactivity. Anything else? Anything else you got? Unsaturated and saturated fats. Oh, good. Okay, that's an easy one. Unsaturated fats have, um, it's not easy. It's a quick answer. Unsaturated fats have no double bonds. Saturated fats have double bonds, except for the carbonyl groups, which are in both of them. So, unsaturated fats are like will have double bonds in the chains, and saturated fats will not. If you look at the pictures here in the lipids section, so these would all be unsaturated because no double bonds in the chains. Or sorry, those would all be saturated, 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 saturated. And unsaturated would look something like this, where it has a double bond as part of that fatty acid chain. Um, and then I don't know if there's really a, I don't think there's a picture in here. But I was gonna say these are kind of like Lewis structures, the line structures, which well this shows pretty well. A saturated fat has a kind of a linear shape because of the bond angles, whereas an unsaturated fat, if it's a standard cis unsaturated fat, the hydrogens are on the same side of the double bond. Double bonds can't rotate, and so you end up with this turned sort of structure or bent structure in the whole fatty acid, and that makes unsaturated fats generally have a lower melting point because they can't pack together quite as efficiently with those double bonds that are kinking the chain like that. So naming the alkanes, it's kind of like functional groups. It was sort of pre-functional groups. So it's this idea that well, let me pull those notes up so we can take a look. So it was these kinds of names. So well, let's start back at the smaller ones here. We made this chart: methane, ethane, propane, butane, going up from there, pentane, hexane, heptane, and then the next three up to 10 are octane, nonane, and decane. So those are the straight chain alkanes. Just if you had a regular straight, all carbons in a row sort of molecule, no functional groups, nothing branching off, what would the name of that structure be? It's gonna be one of those 10 names. Most of them go along with the number, like pentane, pent 5, hexane, hex 6. But the first four have their own special names, so those just take a little memorization: methane, ethane, propane, and butane. Anything else from anybody? All right. Well, as usual, you can send me questions on Discord or via email. And I will see you Wednesday at noon in our normal place, normal time for the final exam. So happy studying, and I'll see you soon. Bye.